Hello everyone, my name is Glen, and today we shall be talking about partial sum. The concept of sequence and series is definitely included in this discussion, and also I'll be including proving by mathematical induction. So I have prepared two examples for today, so let's start. Consider the sequence a sub 1, a sub 2, a sub 3, a sub 4, up to a sub n and infinity. Then the sum S is equal to the summation of a sub n as n starts from 1 to infinity, which is equal to the sum of all the terms. So we have a sub 1 plus a sub 2 plus a sub 3 up to a sub 1 and into infinity. So that's the infinite series. Under this infinite series, we can actually take the partial sum. So the partial sum now is in this concept. We have S sub 1. This would be the sum of the first term, or definitely it's the first term. S sub 2 is the sum of the first two terms. That's A sub 1 and A sub 2. Same goes with S sub 3, the sum of the first three terms. S sub 4, the sum of the first four terms. But the nth partial sum, that's S sub n, would be equal to the sum of a sub 1, a sub 2, a sub 3 up to the last term, that's a sub n. So let's start with example number 1. Find the first 5 partial sums and the nth partial sum of the sequence a sub n is equal to 2n minus 1. So let me write the sequence here. I have my braces. So if n is 1, that would be 1 times 2 minus 1 is 1. If n is 2, that's 4 minus 1 is 3. N is 3, that would be 6 minus 1, that's 5. If n is 4, that would be 8 minus 1 is 7. If n is 5, that would be 10 minus 1 is 9. Okay, so that's my sequence. Now let's start with my partial sum. S1 is the first term. S2 is the sum of the first two terms, that's 1 plus 3. And I have 4. S3 is the sum of the first three terms, so that's 1 plus 3 plus 7, or that would be 5, and it's equivalent to 9. S4 is 1 plus 3 plus 5 plus 7, and that is 16. So I can actually see a pattern here, the relationship of the subscript and the sum. If it's 1, that's 1. If it's 2, that's 4. If it's 3, that's 9. If it's 4, that's 16. So I think the pattern here is the square of the subscript. So if I go for S5 or S sub 5, that would be 5 squared, which is equal to 25. If I do my calculation, that would be 1 plus 3 plus 5 plus 7 plus 9, the sum of the first 5 terms. It's exactly 25. Therefore, my nth partial sum, that would be Sn, is now equal to, basing on my pattern, that would be the subscript squared. So if I write the equation, that would be 1 plus 3 plus 5 plus the nth term 2n minus 1. Add all this, I always end up with n squared. That is what it's trying to say. Now, how can I be sure that this equation is correct? We can do this by mathematical induction. So show that this equation is true. This is what we solve. The nth term is n squared. The sequence a sub n is 2n minus 1. So by mathematical induction, we have 3 steps. The first step is to prove true for n equals 1. Second step is to assume true for n equals k. And the last part is the proving part. Prove true for n equals k plus 1. So let's show. Prove true for n equals 1. That's the first step. So if n is 1, that would be n multiplied to 1 minus 1. That's the nth term. It's now equal to the partial sum, which is n squared. And that is 1 squared. I have 2 minus 1 is equal to 1. I have 1 is equal to 1. Therefore, this is true. First step is done. Second step is to assume true for n equals k. So we simply do the assumption that 1 plus 3 plus 5 plus dot 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 plus 2k minus 1. So we now replace n to k is now equal to k squared. Second step is done. So that we could utilize this for the third step. Prove now that it's true for n equals k plus 1. So let me write the equation again. 1 plus 3 plus 5 plus 2k minus 1. And then this is the last term. We now add another term, which is k plus 1. So that's plus 2k plus 1 minus 1. That's the left side of the equation is now equal to the right side, which is k squared. Now I have add a term on the left side. I shall also do this on the other side. So that's plus 2k plus 1 minus 1. To continue my solution, I'm going to manipulate the right-hand side. So I'll leave the left-hand side as is. So that's left-hand side is now equal to, simplify this, I have k squared plus 2k plus 2 minus 1. Then we simplify 2 minus 1. So that this is k squared plus 2k, and this is plus 1. By factoring, we can simplify this trinomial. So I have k plus 1 multiplied to k plus 1. And note that n is equal to k plus 1, so we can replace k plus 1 by n. So we have now n multiplied to n. And this is equal to n squared, which is exactly our right-hand side on the given equation, which is what we're trying to prove. So once this result come up, therefore, we can now conclude that the equation that we made is true, that 1 plus 3 plus 5 plus the last term 2n minus 1, the sum of this term is always n squared. Now there's another way of solving the third step. Aside from manipulating the right-hand side, let me show you how to do it if you simplify the left-hand side. So again, third step. This is the original equation. Now we can simply change n by k plus 1. So we have 1 plus 3 plus 5 plus 2. And then the value of n would be k plus 1. Then minus 1 is equal to the right side. And now is k plus 1 squared. So I'm not going to work on the right side anymore. Instead, I'm going to simplify the left-hand side. For me to do that, I'm going to bring out the term before this last term, which is 2 times k plus 1 minus 1. So the term before this would be 1 plus 3 plus 5, bringing out the term before this last term, which is simply 2k minus 1. This is the term before this. So plus 2k plus 1 minus 1 is equal to k plus 1. I did not add any term. Instead, emphasize that before this last term, there's another term which was not written. So I needed that because I'll be utilizing the assumption that this left side is equal to the right side. So if we replace this by k, we are now dealing with this value. This value is equal to k squared. So that is k squared plus 2k plus 1 minus 1 is equal now to the right-hand side. And simplifying the left side, that is k squared plus 2k plus 2 minus 1 is equal to the right-hand side. Simplifying this, I have 1. So k squared plus 2k plus 1 is equal to the right-hand side. And then by factoring, you end up with k plus 1 squared, which is the same as the right-hand side. So therefore, it's still true. We now proceed to the second example.